Cool. How's it, everyone? Morning. This is a bit of a rocky start to the morning, so not the ideal way to begin, but I get the sort of honor of going first. So I thought I'd open with a joke for all the sort of chemical engineers, if there are any. But then I was worried it wouldn't get a reaction, so I'm not going to go with it. Cool. Yes. Now you see, everyone's engaged, right? You want to start out hating me. It's wonderful. So I've got this glorious task. I thought I'd do a talk on SF. And SF in 20 minutes is an impossible task. I want to give you a flavor. I want to give you a taste of how cool this package is and why you should definitely be trying to learn it. Yeah, I think let's just jump in. So I'm from a company called IcePack. I'm not going to tell you anything about the company. If you want to know about it, come chat to me. Okay. Cool. So for those of us who never really get past the first page of anything that you've Googled, the too long didn't read for this is basically SF is tidy-like. It's really cool. It is going to replace SP. If you've ever done anything to do with spatial geometries in R, you've used SP at some point. SP is dead. The people that wrote SP realized where they went wrong and decided, let's just write a new one. We'll call it SF and we'll apologize later. Okay. You won't be wasting any time learning how to use this package because it's going to fall into the rest of your workflow if you have a workflow. And it's fun because it's tidy and it's nerdy, right? There's kind of subtle things that the guys have done in this package that you really appreciate, right? When you kind of look under the hood. So as a quick overview, I'm going to give you an overview of some of the geometric primitives. Some geometries in R using SP, so for those of you that have done it before, what it kind of looks like. Some SF basics, some worked examples. If we've got time at the end, which we might not, we'll just cut it to sort of speed things up. Some questions. Okay, so why do we need a package? Geometry is not so hard. Like Euclidean geometry has been around for thousands of years. Like, why on earth do we need a package, right? And the truth is that the Earth is not round. The Earth is a spheroid, right? Which is true. It's part of the truth. It's actually an oblate spheroid, which means it's fatter around the equator. Okay? And the truth is, once you do a bit more digging, you find out even that is a gross approximation of the truth. We are all on a spinning potato. Okay? When you accentuate it a bit more, you find out that the Earth is really none of these things, right? And all of these models, when you deal with spatial data, are trying to find a concise way of approximating what the surface of the Earth is doing at different parts on the Earth so that we can get good distance measures out, typically speaking, right? So part of it's about distance, but there's other parts to it too. Okay. There's lots of different ways of projecting spatial data, right? Lots of different coordinate systems. This is like a work in progress. This is kind of a measure of humanity's effort at trying to describe the potato. Okay, so I'm going to talk about. We'll cover this WGS84 sort of near the end. But as a fun throwaway, this UTM at the bottom here, this Universal Transverse Mercator projection, is fundamental to every tile server. So if you've ever gone on Google Maps and you're on a slow connection, you see those tiles loading one by one. UTM actually defines the indexes for each of the tiles. It's a really concise way of converting the whole of planet Earth into a grid. Right? Super cool. So you're using it even if you don't know it. It's really nice. Okay, so some geometric primitives. This is going to seem really obvious, but it's kind of its simplicity that gives it a lot of leverage. We've got points. Points are just, okay, so points in general, 2D or 3D, could be 2 features, 3 features, or geometry is defining the point. We have lines. Lines, typically 2 or more points, can be as many points as you want. We also call this a line string, technically speaking. I've got here like points and multi-points and lines and multi-lines. You'll see how this ties together. And lastly, polygons. So polygons are like lines, except the end sort of meets the start. And that gives it this property of closure. So you can think of it, it actually has a space that it now occupies. So you can think of like a bow tie. If you have a round polygon and you just turn it in the middle, that's still one line string, but you could sort of get these 2 parts of the polygon, which is quite nice. I've left a couple of links in the presentation just to show you if you know SP and you want to migrate over. This is there's a whole mapping of functions there that the guys have provided. Okay, so this is straight out of the SP documentation. There's nothing fancy about this. This is to show you how to make some spatial points. Okay, so we're going to randomize some numbers. I'm not going to focus so much on the code, but we sort of say make spatial points. And we look at the structure of this object, and you get something like this. Okay, it's a bit icky. Turns out this is an S4 class. Okay, so when you look at it, it's really not pretty. There's like coords, a B box, bounding box, and a proj4 string, which is the projection system. So S4 is it's a reference class system in R. It's got its place. It doesn't work so well with SP, and the reason is if you ever want to get to any of the sort of attributes inside that object, you have to use the @ sign. So already now you're going like dollars and ats, and this doesn't really gel well with anyone's liking of R. So if you want the coordinates, you say xy.sp at coords, right? And that pulls out that slot. So now if you're like me and you really like using dplyr, all you want to do is use that pipe operator and select something within the object. You get this wonderful error message, right, telling you, I don't know how to work with something called spatial points. And you're like, thanks for not being compliant with the way we like to use R. Okay, so that gets awarded a yuck. That's really not cool. So you can do this. You can attach additional columns to the data frame, which is quite nice. So there's our coordinates, and there's more stuff. And there's something really subtle about this if you just look at it, is if you look at every row here, I've got some sort of value 1 and value 2, but the actual column name itself determines what's inside the column. And this is the fundamental assumption that breaks everything about the way that SP works and makes it really bad, is that the rows are not independent of the columns. Okay. So all of a sudden the type at the top here is actually determining what's in it. Bad. Very bad. Okay. So it's not half bad in that we can attach a column, but this is where it gets really bad, is when you want to do joins. So let's say I've got this data frame on the left and the data frame on the right, and I want to do some sort of join between these two on this column over here. So if you're writing dplyr, you'd say, well, S left join with the stuff on the right, and you get an error message. And you say, Rob, you're being lazy now. You know you have to use that @ sign, right, to get to the data. And then you can get your join out. Cool. It just looks really ugly again. But the bigger problem here is that the coordinates column over here did not track with the rest of the data frame. We lost our coordinates. So cool, we can join data, but you're going to lose all your spatial information. Okay. So this is what the guys realized was really bad about SP, is that SP sort of came before dplyr, and then dplyr changed the way that we sort of work from an efficiency perspective. So yeah, there's not a lot to like about SP, just because we know better now. There are a lot of very useful SP functions. You should definitely but they all have mappings now to SF, which is kind of cool. If we don't have an alternative, we'll use it, but SF is this alternative. So it really, SF adheres to the tiny manifesto, which is basically program it nicely, reuse the stuff that's there, don't try and reinvent the wheel. So, and SF meets all of these requirements. Okay. So SF stands for simple features. It uses well-known text, which means when you look at stuff, you actually know what everything is, right, out the box. When you look at geometries, it supports well-known binary, which means you can pull in shapefiles, esris, whatever. It actually makes it embarrassingly simple. It's tidy compliant, so it implements the data frame throughout. Okay. And we can move between the different geometry types. So, like I said to you just now, when you saw those 3 pictures, we've got a point, a line, and a polygon. We can actually move between these types. Okay, so that's effectively what SF provides us, is the ability to coerce between different geometry types. This one on the right over here is called a geometry collection. That's the kind of like try-catch block for if you want to try and mash a whole bunch of whatever's together into one sort of location in your data frame. I'm a big fan of trawling issues on GitHub for finding, so this image actually is not documented anywhere else except on a bug report by someone. So it's kind of nice just to go through what were the bugs that people were having, because all of a sudden you really find out what the community is facing as an issue, which is quite cool. Okay, so we're going to do something really trivial, but I want to give you a sense of how simple this is. So we're going to make points. So this is the most complicated line of code, right? We're going to say, you know, ST is this the spatial type geometry. ST as SF as a simple features, X, Y, my chords are X and Y. Okay, so this is the ugliest line. After this, it gets really simple. So you can see here, the column is called geom. I called it geom. I used the dollar operator. I used everything else that we've used before. Super clean, right? And if you look over here, the point actually embeds the type. So the column doesn't know anything about what type of data is stored in it. Every row is independent of every other row. That's the tidy way. Okay. So this is really nice. We can see we've got all these points. Okay. Ooh. Sorry, there we go. So if I plot this, I can use the base R plot, and I can tell R to plot the geometry column. R knows how to do that. Very nice. If you're like me and you like ggplot, you say ggplot my data, and you say plus geom SF. Now, I didn't have to say geom point or geom line or specify the geom that I'm adding onto the ggplot, because the data frame itself knows what the geometry is that's in there, so it can plot points. Okay, kind of makes sense. Kind of makes sense. So we're going to make some clusters. So I've just labeled all the data 1, 2, and 3. I just ran some k-means. It's nothing big and fancy. But what is interesting here is you can see I've attached this cluster column over here. And what we're going to try and do, so actually, we're short on time. I'm going to suggest you have a look at just what the definition of the feature geometry, and the whole row. So SF works on this kind of paradigm of these are the 3 key important pieces here in terms of how you treat your data table. So there's the special column over here, but it's going to look like every other column in your data frame. Okay. The transformation, and this is the key thing that I want you to take away from this, right? When you do a standard piece of dplyr, let's say you do a group by. I want to group by cluster 1, cluster 2, cluster 3. Okay. When I do this, I would normally apply some sort of summary function, let's say over column Y, right? I'm going to create the mean of y for each one of the partitions and produce a new data frame that looks like this. And what SF does is SF fills the gap that says, I want to do the same thing, but I want to do it on the geometry column. I want to create some sort of new geometry on the right-hand side there that's some compression of a higher dimensional row into a one-dimensional thing, right? So as an example now, we're going to use, thank goodness, pipe operators, nice and clean. We're going to group by cluster, summarize, and tell it to union the geometry column. So take all those points and make it into a union collection, which is just one collection of a multi-point, right? So this is nice because we end up with this, which is exactly what we want. Cluster 1, 2, 3, and a set of points for each one of those clusters. So the next step that we can do then is we can say, well, now take a convex hull and apply it to that geometry column, right? And plot it. So now, nice and simple again, we get a plot that looks like this. That's really clean, right? It's a nice way. We didn't have to wrangle geometries, didn't have to make temporary data frames. We could just work with it, right? Okay. We can make centroids, and I thought I'd give you an example of a line string, but it's a bit complicated. But effectively, you can just union 2 points and then coerce it into a line string, and it's like, oh, okay, I guess I can do that, and it does it, right? Kind of, it's like dplyr, it doesn't complain much. So you can very easily, in the same way, go ahead and create, and you can see here, I'm just using ggplot and geomsf, 2 different data frames, and I said, color this one by cluster, right? So again, now grammatically, everything actually reads really well, but we're doing some complicated stuff behind the scenes. I'm a big fan of VORONOI tessellations. If you've never heard of VORONOI chart, look it up. It's super cool. Kind of gives you this idea of ownership or who's closest to what. But just to take you through the process, if you take that same geometry column from our cluster data and you union it, you collapse it all into one big multi-point column, right? Because we didn't specify a group, but we didn't specify a partition. So just make one big multi-point. You take that, apply a VORONOI algorithm to it, also comes free out of the SF package, and you get this geometry collection, that ugly thing I warned you about earlier. But don't worry, they've got a function to effectively strip that away, give you a set of polygons. You can coerce that into a data frame, and then from there coerce it back into a spatial data frame. And we end up with this very pretty picture, right? So we can combine that with the stuff that we've already got, and you'll see what's really nice here is I've got 4 geom-SF plots now, except over here I'm using from data frame XY a column called VORONOI, and from this data frame in XY a column called geom, right? So now I can actually tell it which columns to use in the same data frame in the same plot, right? Which comes out looking like this. And this is very pretty. So now you can see for each cell all the space around the cell that's actually closest to that cell, how the cluster line is actually divided. If you're writing a k-means algorithm and you're looking for a nearest neighbor, this is a visualization of how the algorithm is actually going to work. Okay. So it was, it's pretty sweet. Shapefiles is a well-known binary. This is even quicker. It's 2 lines. You tell it, read in the world, and you get that. And you're like, wow, that was easy. Cool. Don't know if you've ever worked with shapefiles before. They're really, really icky. It's nice not to have to do anything. And you can see on the table over here, we've got the name of every country as a row. And on the right here, this multi-polygon. So this is, countries are not one polygon. They're lots of polygons. Like we've got South Africa, and then we've got Robben Island is like this little polygon on the side. And we've got a couple of other islands that we own. And yeah, so lots of countries are sort of broken up into multi-polygons. There's your projection string. So now, up until now, we've just been dealing with planar data. We haven't specified the projection. But now the projection comes as part of the data, which is nice. And it tells us we're using the WGS84, and we're projecting onto a long lat basis. Cool. So we say ggplot the world, and fill by area, right? Okay. And you get that. And I like fall off my chair at this point. This is so cool. You just think, wow, this is amazing. Like, in 2 lines of code, I don't know how many other systems you work with where you can get this much traction with so little effort, right? It makes us look good, which is great. So then you can transform it. So you say, transform the world. I should have put a better joke in here, like make the world better, like better world or something, I don't know. But so I just said to reproject it onto a longitude of 25 and minus 28. And if you know your long lats, you know that's about Joburg. That's where I'm from. So it just says, cool, I'll shift the whole thing around and convert and turn. And wow, we didn't have to do any work, right? It's just so nice. Okay. If you like Leaflet, I love Leaflet. Leaflet's very cool. 5 minutes. Nice. Awesome. We're on time. This is just a really simple highlight function. So you tell Leaflet, add tiles, add some polygons. Data is the world. And I want you to put in the label the name of the country. So here you can see you pretty much plot it. And now you have an interactive plot where you can go through and highlight all your different countries and see all your shapefiles and do fancy stuff, right? The point is one common interface. We've got SF works with base R, ggplot, and Leaflet. Basically, any of the major packages all support the SF format. This is why I say you're not going to be wasting your time. As a last example, this is a really, again, off the issues list. This is super cool. a nice way of representing election data is the actual physical geographic boundaries of countries is often not that interesting. And so instead what you do is you sort of raster the whole thing into the set of hexagons where you can see approximately how things are connected, but you're not so much interested in the shape. But what you can then do is you can associate a state, and this is obviously a map of the US on the left, a state with each one of these cells. And what you want to do is group by that state and merge it all together. So SF is clever enough to pick up that all the lines that touch one another along these hexagons are actually overlapping. So it removes them and creates one bigger polygon that you can then visualize. So this is a really neat kind of plot that you can then produce where you're merging together polygons into bigger objects, right? Okay, cool. I'm not a salesman for SF. I don't have shares. But I feel like I have to spread the good word when you find it because their documentation is rubbish. It's very, very difficult to get going. But you have to know that there's this carrot at the end that makes it all worthwhile, right? So for me, the measure of an R package is always, if it's good enough for Hadley, it's good enough for you, okay? And that's for real, because Hadley Wickham is very involved in all of the comments on resolving the issues with the package because it's tidy compliant. And as the kind of, I'd say, core component in the tidyverse, yeah, he's definitely bought into it. Cool. I think we've got probably like 1 minute for questions. We can keep on time. Okay. Cool. Sorry, that was really quick. If you feel overwhelmed, I'm going to set up a GitHub repository with all of these examples so that you can just look through them and play, and then you can get sort of comfortable with it if you want. Yeah, how's it, Hanjo?
Right at the beginning, thank you. Right at the beginning, you create a new column by using sort of the old school dollar operator. Does that sort of, I think it was st_geometry or something, does that work with mutate? So you create your data frame, pipe it into mutate so you could get your coordinates in one go. Into mutate. Yeah.
Yeah. So the nice thing about the terrible thing about SP is that it doesn't work with any of the dplyr functions, the mutates or anything. But you can, effectively what you're doing, if you're not using summarize, you can do a transformation on like a union point thing into, mutate it into a line string or mutate into whatever. So all of the standard keywords that people are already comfortable with all actually work in SF. So you don't have to change the way that you're working. You just add a couple of functions to your arsenal. If you think of it like that, yeah. That's a good question. Oh, okay.
For somebody who hasn't used either SP or SF, but occasionally like bumps my head against wanting to do some geographic stuff, is this a good choice? And also, can you give an application type of like, where do you think this is best used?
Oh, okay. So two parts. I mean, the one is if you've never used SP or SF, you're the luckiest person in the room because you can't make the mistake of wasting time with SP. Yeah, I think you just jump straight in and you learn SF. I mean, that's the simple way. You get a lot for the effort that you put in. The applications for this, I didn't show you any of the distance functions, but where things get really annoying is South Africa, we're kind of fortunate in that you can take our longs and lats, do a Euclidean distance, multiply it by 110, you get approximately kilometers. If you all of a sudden start working with Australian data or data in the UK and you do that same thing, you're way out in terms of all your estimates. So you can do a crude approximation, but where it gets really interesting, if you work a lot with GPS data or spatial data, or anything on the surface of the Earth, you want to be leveraging, there's an st_distance. That will give you either matrix distance or vector distance between any 2 points or whatever. So that's really where the application area gets really interesting, is when you're actually analyzing data and you're trying to make the distance calculations between things on the sphere. Cool. Thanks.